Okay, so next up we have Herminso Gómez. Hope I'm pronouncing that okay. We're about 4 minutes fast. I can give you some extra time, or you can hang out for a couple of minutes in case somebody wants to come in right on time.
I can start the thing up.
Yeah, okay. So Herminso is going to talk about quality assurance.
Thank you, Jason, for the kind introduction. Let me start by removing away the barriers between you and me. Let me see. Okay, once I see my slides over here, I get started. Okay, so today rechargeable batteries play an essential role in the world we live in, to the point that almost every major automaker has announced a transition from combustion engine cars to electric vehicles in the next 10 to 30 years. One of the biggest challenges facing electric cars, as we might have heard of, is their batteries. They face different challenges in terms of manufacturability, performance, load capacity, durability, and safety concerns, and pose other challenges in terms of quality inspection and failure analysis. Most battery cells in the automotive industry can be divided into 3 packaging form factors: cylindrical cells, prismatic cells, and pouch cells. This slide shows a list of the main features that people are interested on for quality inspection or failure analysis. Per battery type, ranging from detecting particle inclusions, cracks on cathodes, overhang, tab welding safety, electrode defects, winding gaps, material delamination, housing integrity, etc. And there are several advanced techniques that can be used for inspecting lithium-ion batteries. For example, visible light. We also have X-rays, electron microscopy, ions, neutron microscopy. Some of them can certainly see inside the battery, but there are some limitations due to measurement resolution, and that's what you can see there in terms of penetration length in the y-axis, and in the x-axis, the wavelength. Basically, the type of features or resolutions that you can achieve with each one of those methods. And while we have the ability to do inspection with a bunch of those techniques, including electron microscopy, light microscopy, and X-ray microscopy, given that my expertise is X-ray, computer tomography, and microscopy, I'm going to focus mostly on that topic today. Also, given that X-rays has the main advantage of being non-destructive, so you can see inside of the battery without opening the cell itself or cutting it apart. And also, from the other plot that you see in the other end, you see the type of techniques and you see the scale of the features in lithium-ion batteries that you could inspect. And you might notice that one of the largest lines is X-ray imaging, covering multiple scales, multiple length scales for inspecting battery cells across from centimeter level for cell level analysis to sub-millimeter volumes for material microscopy analysis. And they capture relevant structural details with a spatial resolution ranging from several tens of micrometers down to tens of nanometers. This is the X-ray imaging workflow with the acquisition process representing both X-ray CT or computer tomography and X-ray microscopy, but with the main difference being that X-ray microscopy has an additional step, which is adding optical magnification before recording the final radiographic images. And that's done to achieve that high spatial resolution. Then an operator selects the settings for scanning the object based on its geometry, size, and composition. The sample rotates while the detector collects projection at different angular positions. And then using software reconstruction, we can create the full, or reconstruct the full volume of the object, in this case a battery, in 3 dimensions. So you see the battery, the full volume including inside features. And then using some kind of software you can do and use cross-sectional views or slices to see inside, to inspect the battery for different types of potential failure or features that you want to investigate. The 3D data is that you can see there is accessed again without destroying the battery. This example, you can see an image of the inside of an 18650 battery, where cracks and as well as voids and imperfections in the internal structure of the battery can be clearly identified over there. You see some kind of particle inclusions and a little bit of cracks. And you see 2 images. You see a low resolution image in a large field of view and a zoom in, which is using one of those X-ray microscopes zooming in to see a smaller field of view, but a higher resolution. Another model in the market is the 21700 battery. And in this video, you'll see the 3D X-ray reconstruction workflow of several portions of the battery using X-ray microscopy with something that we call resolution at a distance, because in reality you're not putting the battery is intact, you're just zooming in into the different portions to be able to scan at a higher resolution a chunk of the battery without slicing or cutting it. And you can see several interesting details over there, including the presence of some particle inclusions, the bright spots. And I think we were able to detect at the end the presence of a crack inside of the battery, and it's coming up in this portion of the video right there, which is segmented apart, so you can see clearly. That might be the consequence of a fatigue operation after several cycles of charging and discharging. So using X-ray microscopy with different sets of lenses and the resolution at a distance feature, images of different resolutions per voxel can be scanned, where voxel here represents a 3-dimensional pixel, because remember, we have the full volume, we have access to the full volume here. You see an image of the full battery at 34 micrometer voxel size, and then portions of interest scan at 11.5 micrometers, 4 micrometers, and 2 micrometer voxel size, where clearly when you start going to higher resolution capabilities, then you see smaller details inside of the battery. And again, all of this has been done without taking the battery apart, and it's volumetric data. You can see details not only at high resolution, but also at high contrast. So you can see low density features on the battery, such as the polymer separator, and some layered details inside of the different materials can be identified. So when you do X-ray quality control with X-ray solutions, there are different modalities, and I have mentioned mainly 2 today: X-ray microscopy, which means you have some lens capability to get high resolution images, and computer tomography. And they complement each other. The X-ray microscopy can give you assessments of materials and high resolution details in some battery cells. But when you start getting into battery packs or modules, then you might run out of power in terms of penetration length and you might have to use X-ray computed tomography with higher kV capabilities to be able to penetrate into the materials. And you see some examples there of scanning a pouch battery, a prismatic cell, and a battery module. And if you want to learn more, you can check the references that is in the bottom of the slide. So that way you can inspect various parts of the battery production process, from cell assembly to battery modules. And here's an example of pouch cells with X-ray computed tomography, which can inspect overhangs, particle inclusions, electrode defects, well tabs, and electrode wrinkles, among other characteristics. Similarly, in prismatic cells, X-ray computed tomography can inspect overhangs, well tabs, electrode defects, metal particles, delamination, winding, electrode burn marks, etc. And in module assemblies, X-ray computed tomography can also inspect similar features: overhang, well tabs, cell defects, metal contamination, electronic components, quality inspect the quality of the tap and bus bar welding, and even dimensional metrology analysis of the battery housing structure. So 3D X-ray computed tomography, though it cannot get to the level of resolution of 3D X-ray microscopy, it can inspect bigger parts, including the full battery packs. And this is some sort of summary of X-ray CT inspection for the cell and module components, highlighting the macro scale features relevant to battery inspection. And I'm not going to repeat, but I already have mentioned some of them that are highlighted in this slide. Okay, that is great, and that's a great summary of X-ray computed tomography and X-ray microscopy. But there are some roadblocks in this type of technique, and generally is related to speed. So now I'm going to present what we are using to leverage artificial intelligence to advance battery research and failure analysis with both X-ray image acquisition to speed up a little bit, and also for CT or computed tomography image segmentation. So let me start with using artificial intelligence in image acquisition. Traditionally, there is a reconstruction technique, which is an analytical algorithm invented in the 1980s, but it takes quite long because it requires a large number of projections. What we are doing to speed up the process is, rather than using the standard analytical reconstruction technique, a network can be created between the 2D projections and the 3D data reconstructed volume, and this is trained in a way to ignore noise in a system while paying attention to features, thereby removing noise and artifacts from the resulting reconstruction. How this is helpful? Because we can reduce the number of projections that then you collect for reconstruction. With the standard reconstruction, the analytical algorithm, you need in the order of 1,000 projections. It's 2,000 or 3,000 projections. If you cut the projections, the problem is you start getting artifacts. Aliasing, the technical term, is basically undersampling. But if you train your model to identify those effects, then you can remove them and recover the data. And that's what we are doing here. Here is an example with a 21700 battery, and this is the standard reconstruction with 3,200 projections, long scan time. If you reduce the standard the projection for the standard reconstruction, then that's why you start getting some artifacts, so you start losing part of the data, and you add noise. If you use deep learning algorithms, now you can use less projections, because granted you created a model with a high quality image first, and then you can reduce the projections to 400 and then reduce scan time. This will speed the inspection of more batteries of the same time, of the same type. Of course, if you change the battery type, you need to create a new model. But this is similar, so you're getting a 8x throughput improvement in this case. And not only you're improving scan time, but you're also improving some of the imaging. If you can see in this example, if we reduce the projections to a quarter to speed up the process, then you see the noise. You see a bunch of noise and that's the effect I was mentioning of cutting the projections or aliasing. And if you use deep learning algorithms, you can see that now we get rid of the noise and we can see clearly the features. And I want to be clear here, this is using deep learning algorithms in the pre-reconstruction phase. And I'm making these clarifications because generally there are people that use post-processing reconstruction in which they try to smooth out the data, but what happens is then they get rid of data. They lose data, especially small particles all around the edges of the surfaces. So that's not happening here. As you can see here, we are recovering the small features of the data, including some of the visibility of the polymer separator that you start losing when you put the projection with the standard reconstruction. Now, that was a way to kind of speed up the reconstruction process by putting projections, but there is another challenge in battery inspection and in general electronics or so, is the compromise between resolution and field of view. You see in this image a large field of view, a low resolution, and if you start getting high resolution image, then you have to zoom in. So you compromise the field of view to a small portion. But what if you want to scan the full field of view at the same level of resolution that you see in the small field of view? Well, there is a solution for that. If we use deep learning again, you can train the zoom in data, and because the data more or less repeat in terms of features, now you can use this deep learning training algorithm to expand to the full field of view, and that also will speed the process. Because if you were trying to do this by the classical approach, you will have to scan at high resolution different chunks and then stitch them together, which will prove too long. And here is an example. This is a somewhat low resolution. I mean, you can think it's a high resolution enough, but if we want to be even better, we can train the data with this even higher resolution portion of the data and expand to the full field of view. So that's a second way of using deep learning algorithms for reconstructing data with computer tomography or X-ray microscopy. We see a lot of benefit in X-ray microscopy, especially because when you start getting high resolution data, the process can become slower. So that's where we see the major benefit. Here is a kind of a summary between the two techniques that I have explained for using deep learning. One is for maintain speed or speed up the data acquisition and improve the image quality for interior imaging. So you focus in a single field of view. You just you're increasing the speed by training the algorithm and putting the projection. But there is a second possibility, which is to achieve high resolution in a large field of view when you train the data with a small field of view and then you expand to a low resolution large field of view scan. And that's about image acquisition, reconstruction, and processing. But there are other ways to use deep learning algorithms, which is for image segmentation. And by the way, that's applied across different fields. This is not just X-ray imaging. The image that you see in the other corner is an electron microscopy. Just a disclosure, that's not an X-ray imaging. But you can use it in electron microscopy, these deep learning algorithms, and also in other techniques like light microscopy or X-ray microscopy. And these are the different ways that we can use. The main question is, how do we get the best image that we can learn the most from in the less amount of time? And a powerful and reproducible segmentation is the mandatory precursor for any downstream image analysis and measurements. If we I'm gonna just show you an example to give you an idea. And this is an example of post-reconstruction. So we are now after the reconstruction phase, when we already have the data, and we think that data is good enough, and if we need to speed up the reconstruction we did, but it's post-reconstruction. And now we are using for CT image analysis or computer tomography analysis for computing the battery overhangs. By leveraging machine learning algorithms, we can teach that the model what constitutes an anode from a cathode, and then the analysis can run automatically and report out the overhang measurements. we can set tolerances and flag parts as pass or fail. Such analysis can be obtained more accurately because you're using a machine instead of a human trying to do those measurements by hand. There are too many, and you can do it faster. The machine is much faster than a person trying to do this. So with this, if you have any questions, I'll be happy to answer.
So if we could get the speakers to come up on the stage.
All right, so let me just start off by asking a question to you, Herminso. So we want to implement these for quality assurance. So right now, how accessible are these things to people who are not experts?
When you mean accessibly, means is this one?
Yeah.
Okay. You mean in terms of expertise, like how to use it? So there are different levels of expertise that you might need, but right now the way it operates is you have systems that are kind of semi-automated, but you still need to do some operator input. It's not fully automated, so you definitely need an operator to try to set the basic scans. And what people do is the manufacturers of X-ray systems, X-ray CT systems or microscopy, they have training sessions of a couple of days to transfer that knowledge. Now, if you start talking about very research topic down to like people doing investigations to university level, yes, you need more training, but that's left to those researchers. The universities, they have the expertise. We have expertise on the technology. We transfer that expertise, but of course we are not battery experts. So it is manageable.
Yeah. Okay. Great. Questions from the audience?
On using the AI to cut down on the amount of measurements you make, and so this is on the last talk, has there been any kind of analysis of, like, I'll say, like an error between, using image analysis or spatial image analysis between the check, which would be 1,000, say, and the 100, versus kind of just doing, it looked like one was just, you just did the straight scan and then used AI. Did that significantly bring the error down? I'm suspicious it is, but I'm just wondering if you have any data on that.
Yes, we have internal studies and we have universities that have published some data, use some of our instruments. And yes, it shows that artificial intelligence improves the accuracy because you have more data. There is no way you can collect enough data to do statistical analysis with just a person trying to do that. Plus you take the risk of human error. Of course, you need to have a good training data. So that's the other kind of problem that you can have. You have to make sure that the training model is good enough for your analysis. So you need to do kind of a comparison between a traditional way of measuring and the artificial intelligence. But when you are confident enough in your data, then you can just run and have literally thousands of data, which gives you more accuracy.
Okay, yeah. So I'm just curious, how much does that reduce the error by using AI? I mean, is there any, or is that's more like academic?
No, it's what type of error in terms of? Give me just an example of.
Well, I'm just wondering if you actually looked at the check, the 1,000 versus the 100, and you actually did like image analysis. Is it something like it reduces it from not doing any AI is like
Okay, so now
60% error and it takes it up to 90?
Yeah, so I think now I understand the question. You're asking specifically when you put the projections to speed up the image acquisition and you get an image that gives you data.
Mm-hmm.
Yes. So, of course, the first thing is you have a faster access to data. So you have the data that is collected with this projection. Second is you have the ability to analyze across the full volume with if you use post-processing deep learning or something like that, you are able to see across the full volume, which is literally thousands of slides in the volume, which it would be much better than a human doing it, because you have to do a slide by, let's say you start from the top of the battery and you start going all the way to the bottom. You take the risk of missing some of those slides. The artificial intelligence is able to do that. Now, there is one more clarification that I want to do. It's what we are doing is making sure that you get the best image. So the artificial intelligence or the deep learning pre-reconstruction is trying to get you the best data that you can have in a shorter amount of time. Now, what you do with that data after is up to you, and you can still use the other artificial intelligence algorithms, but what we want is to have the best quality data to start with for the analysis.
Okay, all right, thank you.